In this video, we're going to talk about the first stars, and we're going to focus in on the fusion processes happening within the bellies of these first stars. Now, this fusion process is what fusion is for all stars that are big enough at all times, and we're reaching this for the first time now as we reach the first star to ever exist. Now, this first star, because it was composed of only hydrogen and helium, it was big enough to max out the fusion that's possible, nature's maximum, iron. But until this point, there had been no elements heavier than lithium, which had been created in trace amounts in the nucleosynthesis of the early universe from 3 minutes to 20 minutes. And it's now, finally, that we begin to have heavier elements. So, how does it happen? What goes on? Here's a periodic table, and there are 118 elements that in existence. That means that there are 118 particle types in which there are between 1 and 118 protons. A number of those have never been found on Earth naturally and have never been made in the cosmos naturally and have just been made in labs on Earth and perhaps in labs on other planets. And some of them, namely many of those between hydrogen and iron, or element 1 and element 26 in row 8, column 4, we'll be covering today. Let's jump into it. For the most part, the story of the fusion in the belly of a star is that of hydrogen into helium. That takes up 90% of the lifetime of a star, and after that, as it fuses heavier elements together, you can see that as the initial dying stages of the star before, in the case of these early stars, they blew up. What happens in the belly of a star that's been fusing hydrogen into helium is that eventually the core is filled with helium, and because it's not hot enough for helium nuclei to fuse with each other, fusion just stops in this core of helium, and that stops the outward pressure of fusion from holding back the gravitational force of the star, and the star comes tumbling in, the center gets tighter, the temperature increases to the point that helium nuclei can now fuse with each other. Once they fuse with each other, they create a beryllium-8 atom. Beryllium-8 is notoriously unstable. That decays into 2 helium-4 nuclei. The center continues to get more dense until we reach the point that a helium nucleus could hit another helium nucleus to create a beryllium-8 atom. And despite its incredibly fast decay, before it decays, another helium nucleus will hit it, and suddenly we have the stable atom of carbon-12. Once we have that, so long as we have a big enough star to bring about high enough temperatures, helium nuclei will fuse with carbon to make oxygen-16. A helium nucleus added to oxygen-16 will make neon-20, and then we just continue to magnesium-24, to silicon-28, to sulfur-32, argon-36, calcium-40, titanium-44, chromium-48, iron-52, and nickel-56, which is also unstable, and that decays to iron-56, having us maxed out at iron. There are other nuclear fusion processes that happen in the center of stars, but this is the main story, this of the alpha particle or helium nuclei being added in the so-called alpha process. So we're going to leave it at that. And instead, we're going to shift to the question of why did we stop at iron? Now, it's a little more complicated than fusion stopping at iron, and we're going to explore that in a later video. But for the moment, let's accept that fusion stops at iron and try to understand why. The reason why is kind of intuitive. When you combine hydrogen nuclei to make helium, or helium nuclei to make beryllium-8, carbon-12, and so on, what you're actually doing is taking a number of particles that are of a certain energy and combining them into a new particle that's of a lower energy. 3 helium nuclei are of higher energy than the composite carbon-12 atom. And what that means is that in the making of this atom, a lot of energy is released. And this logic continues, but it only continues up to iron. Once you reach iron, adding iron with iron, for example, will give you a particle that actually has more energy than the 2 iron particles that made it. So you can't do that. You can't force 2 iron particles together and make a heavier particle than the 2 irons together are. You need to add energy to that system, and we don't have enough energy being added in the center of the star, so that's not happening. And that's why it peaks at iron. If you found value in this video, please like it. And if you'd like to know everything, definitely subscribe, check out the channel. We're here for big history. We're here to learn and know everything.